All right. Somehow, way down here, it's not in the energy thing. They've got should be just powers work over time. Okay, should be, in my opinion, in my humble opinion, it should be in one of the sections. It should be in work, energy, and power, but it's not. So it should be in section 2.3. But it's not, okay. And then they show it this way, which is fine. Energy and work are really pretty. Anyway, it's just weird. And then this is power again. Remember, power is in joules per second, so it's the rate at which you're doing work. Watt is another way to write joules per second, right? Then they have this, and this is for turbines, wind turbines. And basically, what it is it's the power that is present in air as it flows over the turbine, right? One way to visualize this, and by the way, they ask you to derive this sometimes, so just like maybe pay attention, right? Okay, so here's this thing, here's this air, right? And basically, it's the kinetic energy of this chunk of air, and this is all the whoops, that should be a dotted line, right? This is that chunk of air that's going to hit a wind turbine, right? So we get the little like that, right? Okay, so it's got a radius like this, right? And that total volume of air, the total mass of air that's there is the density of the air times the volume of the air, right? The volume of the air is, it's rho, and then the volume is pi r squared times whatever this length is of this, right? Of length. And then the kinetic energy of this thing is going to be, the kinetic energy is going to be 1/2 mv squared. Right, so it's 1/2, and then the mass is density times pi r squared times that length, right? Times whatever the velocity of this chunk of air is, right? It's moving this way at some speed, right? Okay, and then that's the kinetic energy. Kinetic energy divided by time is energy divided by time, right? So that's our power. So if I divide this by time, I'll get power, right? And then there's one last thing. Notice that we've got L. How long this chunk of stuff is, divided by the time it takes to hit, that's another V, right? Okay, and so we've got, if we simplify this, we got 1/2 rho, and then instead of pi r squared, I'm going to say area, right? Instead of this L over T, I'm going to put a V, and then a V times V squared is V to the third. And that's our power. All right. Hopefully they won't ask you to derive that, but anyway, there it is. So this is the area of the frontal area of the turbines, right? Probably it's pi r squared, but you could have one of those helical turbines, right? That you've seen them. They look like an egg beater or something like that, where the things are. I don't know. I can't draw it. Yeah, I can't draw it. But anyway, it could be like just rectangular area too. And then this is the density of the air. This is the velocity. Now understand that air contains a tremendous amount of energy. This thing isn't going to be able to make the velocity stop. So typically what's going to happen is you're going to have, it comes in at some velocity, it leaves at some velocity, so the power will then be 1/2 rho area, and then you'll have to go velocity of the third minus velocity of the third, and this is the incoming, outgoing. And if you think about a windmill like that, it really isn't slowing the air down that much, right? It doesn't slow it down to a stop. You never get all of this. So this really is just the energy that's in that air, or the power that's in that air, right, for a certain frontal area. And then this thing might also have an efficiency, right? So even though you've got this, that's theoretically what's available to the thing, and then you might have to multiply it by 0.8 if it's 80% efficient.